Alright, this is the sixth installment to our Unit 3. This is about circular motion. Now, I just want to say about circular motion, there's not a circular motion calculation that you'll have to do. You have to be able to understand what causes circular motion, which, if you think about back to the vector assignment and the ladybug going back in the circle, you all answered this idea already. So just try and remember that as you're listening to the video. So, think about this situation here. So if we've dropped an object, it goes straight down, and if it's thrown, we know it goes horizontally as well as going down vertically, creating a curved path. And because the acceleration is always pointing downward, just as we always have learned. Now that's what we've been doing on the surface of the Earth. Let's take things big scale and think about dropping something, comparatively to the Earth versus throwing it compared to the size of the Earth. What do we think could happen? It's still going to take that curved path because gravity is still pointing down for the object. But remember that is pointing towards the center of the Earth at every given moment on the surface. So it's always pointing to the center of the Earth. We just don't think of it like that because we can't really perceive the curvature that the Earth has. But we can calculate it. And we have ways of visualizing it. So we actually do know approximately, this is very approximate, assuming there's no flat or mountains or anything like that we have around here, but the surface of the Earth curves at a rate that it goes about every 8 kilometers horizontal. It's dropped vertically by 4.9 meters. So think about standing on the edge of a ball. It takes 8 kilometers for the edge of the ball to be down 4.9 meters. So if you're standing right here, this is 8 kilometers away, and this is only a distance of 4.9 meters. So it takes a long time for it to drop, which is why we don't perceive that drop and curvature of the Earth. But the question that we want to talk about is how long does it take an object to fall 4.9 meters? So here's our time, is what we're looking for. We know our dy is 4.9 meters, and ay is negative 9.80 meters per second squared, and v naught y says it's fired horizontally, which means v naught y is 0 meters per second. We're not given vx, but we don't need it. What we're looking for is time. So if we use our equation dy equals v naught yt plus 1/2 ayt squared, this part goes to 0 because the v naught y is 0. We get dy equals 1/2 ayt squared. Rearrange for time, plus or minus the square root of 2 dy over ay. And don't need to worry about negative times, so we get 2 times 4.9 meters over negative 9.80 meters per second squared. And again, it's so easy to miss that important negative, because right now we couldn't solve this problem. Always remember, if the distance that you're going, that you dropped, is a drop, that has to be negative, even though it's not given as negative in the problem. So that's a negative 4.9, so our negatives cancel out, so now we can square root it. And we get a time of 2 times 4.9, which is 9.8, divided by 9.8, which is 1. Square root of 1? 1. So we have 1.0 seconds. Okay, that's interesting. So it takes 1 second for it to drop 4.9 meters. Now here's our question, and think about this situation. If a projectile was fired horizontally at 8 kilometers a second, what would happen? So think about that. So in that 8 kilometers, so it's gone 8 kilometers this way, and it's gone in 1 second, it would drop 4.9 meters, just like we just said. So an object takes 1 second to drop 4.9 meters. and then it would go another 8 kilometers and drop another 4.9 meters. Well, imagine if we had just a circle. An object like this would keep going around the Earth, and it would never actually hit it, because the Earth is moving underneath it at the same rate that it is falling. So the curvature of the Earth matches the curvature that the bullet would have, which is very, very interesting. And this is exactly how everything stays in space. Satellites, the moon, everything stays up there because it's of this continual motion around the Earth. So the question is such an object accelerating? If we're just looking at that first second, it has to be accelerating because it's in gravity. It has an acceleration caused by gravity. So yes, it is accelerating. How do the directions of its velocity and its acceleration relate? Gravity is always pointed down, but really that means it's pointed towards the center of the Earth. So acceleration points to the center. Now we can think of Earth, but it would be the center of any circular motion. The acceleration will end up pointing towards the center. And then our velocity is always 90 degrees, so it's perpendicular to the acceleration. And that's what causes circular motion. When it is perpendicular to your acceleration, you end up going in a circle, as long as the acceleration direction keeps changing. So at any point, both values are changing their direction, but the magnitude is not going to change. Is the moon falling? We can think of the moon as falling because all it's saying is that it's being attracted to Earth because it's gravity. It is in Earth's gravity field, so it is attracted to Earth, which is being pointed towards the center of the Earth. As it goes around, it is just staying a certain distance away because it's at a particular speed that matches the curvature of its path around the Earth, so that it moves and is pulled towards the Earth at the same rate as at the shape of the Earth. So the path and the shape match. And that's the same for any satellite. The International Space Station, every GPS satellite, every phone satellite, any object in space is technically falling. It just doesn't get any closer because of how the curvature and the path of the object are matching. This is called centripetal acceleration. And that is when an object traveling in a circle at a constant speed experiences acceleration toward the center of the circle. So our v is constant. So v here is constant, even though the velocity, the direction is always changing, the value of it is the same. And so towards the center of the circle, and the velocity of the object is always tangent to the circle, which has two properties. The direction of the velocity or the speed is constant and the direction is changing. Therefore, it is accelerating. So the speed is the same magnitude at all points. The acceleration is the same magnitude, but it is always pointing towards the center of the circle, and the velocity is perpendicular to that at all points in time. So those things are both changing. So you don't need to know any calculations for this, but you need to get those ideas. There are some conceptual questions in the textbook. Check the problem list to see those, and we can talk about them in class. And as always, physics is still awesome.